Can we fine-tune verification to acknowledge and validate non-aligned responses? This inquiry is motivated by the LLM as a judge paradigm, which has shown that large language models can effectively evaluate answers in a flexible manner. To replicate this capability in our target model, a bespoke dataset is constructed that encourages the model to produce informed assessments of the current continuation. By training a lightweight module atop the embeddings, it empowers the model to render verdicts on the ongoing dialogue. The approach is exemplified through its application to the Llama 3.1 family, where the 8B/405B judge variant achieves a notable speedup of 9 times over Llama 405B, while maintaining its performance across a diverse array of benchmarks. To comprehensively assess the efficacy of the verification approach, a thorough evaluation on a diverse range of benchmarks commonly employed in the field of speculative decoding research is conducted. Specifically, the analysis encompasses the GSM-8K dataset, the HumanEval benchmark and the MT-Bench evaluation framework. In contrast to traditional SD studies, this verification strategy necessitates the reporting of accuracy metrics, as the process of adapting verification inherently involves the risk of accepting incorrect tokens, which can lead to diminished performance. To provide a more nuanced understanding of our approach, multiple-choice benchmarks, including the ARC dataset and the MMLU evaluation, are incorporated. These atypical tasks, which require the production of only a few tokens, serve as a valuable check to ensure that our verification scheme does not compromise performance. The efficacy of speculative decoding methods in achieving end-to-end speedups is largely contingent upon two primary factors: the number of tokens accepted and the latency gap between the draft and target models. Notably, the latter factor is heavily influenced by the implementation of orthogonal inference time optimizations, such as quantization, model parallelism, and graph/kernel optimization techniques. Regrettably, the majority of prior works on SD have relied on the user-friendly, albeit unoptimized, library Hugging Face to implement their methods. However, the reported speedups of prior SD methods in Hugging Face tend to diminish significantly when transitioning to optimized inference frameworks. For instance, the acceleration of Eagle on Llama 2-7B drops from 3x to a mere 1.5x when utilizing GPT-Fast. In fact, vanilla Llama 70B, without any speculative decoding, exhibits a higher throughput in GPT-Fast than the state-of-the-art SD method Eagle 2 does on the same model in Hugging Face. In speculative decoding, the goal is to generate multiple candidate outputs quickly while maintaining high quality. This is achieved through the collaborative functioning of two distinct models, the draft model and the target model. The draft model is responsible for generating a diverse set of candidate sequences in parallel. Its primary objective is to explore various possibilities without being overly concerned about the accuracy of each generated output. The draft model operates with a focus on speed and creativity, allowing it to produce a wide array of potential sequences rapidly. The draft model may use a less complex architecture or operate with fewer computational resources to expedite the generation process. In contrast, the target model is focused on quality and refinement. It takes the candidates generated by the draft model and evaluates them based on their likelihood and relevance to the specific task at hand. The target model aims to select the best candidates for further processing or final output generation. The target model is typically more sophisticated, employing advanced techniques such as attention mechanisms or contextual embeddings to assess the candidate's quality. This two-step approach, first generating a pool of candidates and then validating them, enables more sophisticated handling of token generation. It leverages the strengths of both the draft model and the target model, allowing the system to benefit from the speed of the draft model while ensuring that the final outputs from the target model are reliable and of high quality. By implementing this strategy, we enhance the overall effectiveness of the speculative decoding process, making it a powerful tool for various language generation tasks. When delving into the realm of speculative decoding, a pressing concern arises: What's the sweet spot for draft token selection to achieve optimal speedup? On one hand, if the draft model consistently produces high-quality tokens, it's tempting to generate a large pool of candidate tokens to minimize the number of expensive target model invocations. Conversely, if a significant proportion of these candidates are ultimately rejected, the time spent on drafting becomes a sunk cost. The ideal number of draft tokens, therefore, hinges on the acceptance rate, which is inherently tied to the verification scheme. To illustrate this point, consider the results presented, where the average number of accepted tokens is plotted. The yellow curve reveals a striking pattern. As the number of draft tokens increases, the number of accepted tokens quickly plateaus, leading to a precipitous decline in acceptance rates. This phenomenon has a profound impact on the efficiency of the inference process. Simply put, choosing an excessively large number of draft tokens only serves to increase the number of unnecessary draft model invocations, ultimately leading to a suboptimal overall performance. Notably, the discrepancy between draft and target models often arises from the target model's propensity to scrutinize responses with an unyielding fervor. Even when the draft model delivers solutions that are technically sound, the target model frequently flags numerous tokens as non-compliant, a phenomenon that persists even when the solution is, in fact, correct. This phenomenon can be attributed to the target model's tendency to prioritize self-consistency over contextual accuracy, resulting in a rejection of responses that, while accurate, fail to align with its own predetermined framework. The investigation into the relationship between response quality and acceptance rates reveals a puzzling disconnect. To shed light on this phenomenon, we conducted an experiment that pitted a high-performing LLM against a state-of-the-art model. By leveraging GPT-4o serving as the draft model and Llama 405B as the target model, we generated comprehensive answers to a range of benchmarks. The goal was to determine whether the quality of responses would have a positive impact on acceptance rates. To ensure that the target model was capable of recognizing the high-quality tokens, the performant Llama 405B model is used. The results, however, defied expectations. Despite the draft model's exceptional quality, the target model accepted only a paltry 2 tokens before rejecting the response. This finding was all the more surprising given the significant difference in quality between the draft and target models. To further explore this phenomenon, we reversed the roles of our standard setup, using Llama 405B as the draft model and Llama 8B as the target model. While this configuration did yield a slight increase in accepted tokens, the overall trend remained the same. Acceptance rates did not correlate with response quality. This observation has significant implications for the development of more effective response evaluation metrics. The conventional approach to speculative decoding relies on the model's confidence scores, as calculated by the softmax function, to either accept or reject a given token. However, this research reveals that the model's response to processing an incorrect token holds valuable information. Specifically, the experiments demonstrate that the last hidden layer embeddings of erroneous tokens serve as a sort of error flag, prompting the model to generate subsequent tokens that attempt to rectify the mistake. Llama 405B on incorrect responses, which are highlighted in red, and observe the model's immediate efforts to correct its response, which is highlighted in green. For instance, when forced to begin with the incorrect statement, "The capital of France is Berlin," the model continues with, "Just kidding, it's actually Paris." This unexpected behavior suggests the feasibility of leveraging the embedding of the current token as a means of verifying its correctness. In fact, we will show in the following that a simple logistic regression head on top of these embeddings achieves high accuracy and can be trained in under 1.5 hours. To fine-tune the model's ability to accurately identify and reject incorrect tokens, a weighted cross-entropy loss function is employed, which effectively mitigates the class imbalance present in our dataset. By assigning greater weight to negative examples, the model would not be overly lenient in its judgments, thereby preventing quality degradation. To prevent overfitting, early stopping and carefully tuning hyperparameters on a small test split is handled. The experiments revealed that deeper layers of target embeddings yielded the best results, with only minor variations observed across different layers. Conversely, shallower layers consistently underperformed, aligning with findings from previous studies. For simplicity and optimal performance, we opted to utilize the last embedding layer before RMS normalization and the language modeling head. In exploring more complex architectures, including multi-layer perceptrons and shallow transformer networks, we discovered that a simple linear head proved to be the most effective choice. This linear classifier offered several practical advantages, including a reduced number of trainable parameters and a training time of less than 1.5 hours on a dataset of 30K tokens. The verification mechanism of speculative decoding is a critical flaw in the alignment between draft and target responses, leading to the rejection of objectively correct continuations. To overcome this limitation, proposed an innovative verification scheme that leverages the versatility of large language models to judge responses. This adaptation enables the efficient drafting of more tokens, resulting in significant speedups of up to 9 times on various benchmarks, with an unprecedented rate of 129 tokens/s for Llama 405B. The research highlights the exceptional performance of small language models exhibited in the regime of many draft tokens, outshining the small modules employed in approaches like Eagle or Medusa. It is anticipated that this trend will continue to intensify in the future. However, this approach also comes with a trade-off. The mathematical guarantee to maintain target quality is sacrificed by relying on the judge.